On this video, we will talk about circles and the lengths of segments. So let's start by just reviewing what we have talked about so far, and I think we can summarize a lot of things given this diagram. Because what are some conclusions that we can draw given this diagram on the right hand side? Well, notice that we don't have neither central angles or inscribed angles, so perhaps we cannot use what we have discussed on those two topics. But we definitely have chords. Definitely, we have two chords here. We have the chord of AB and the chord of CD. So now let's think about what do we know whenever there are chords involved. Well, notice that by doing those chords, we definitely have created some other angles. Let's call this angle 1. Let's call this angle 2. Let's call this angle 3. And let's call this angle 4. Well, I know that there's a relationship between the angle and the opposite arcs. Because according to yesterday's lesson, we know that angle 1, it's equivalent to half the sum of the opposite arcs. So therefore, there's one thing that I can say about this diagram, and that is that angle 1, it's equivalent to 1/2 of AC plus dV. That's one thing that I can say about this diagram. Is there anything else that I can say about this diagram? Well, notice that angle 1 and angle 3 are vertical angles. So therefore, angle 3 it's also equivalent to 1/2 of AC plus dV, because there must be congruence since they're vertical angles. Now, is there anything else that I can say about perhaps those two angles, angle 2 and angle 4? Well, notice that angle 2 can also be seen as half of the opposite arcs. So therefore, angle 2 is equivalent to 1/2 of AD plus CV. But angle 2 is vertical to angle 4, so therefore angle 4 it's also equivalent to 1/2 of AD plus CV. And I think this is all we can say about this diagram since we have not been given any numerical measurements in this figure. One thing to notice that I knew that this angle, or at least this point, is not the center of the circle, because here this will be the center of the circle. So therefore, I cannot think about this angle or any of these angles as if they were central angles, because the vertex is not at the center. So I can use what we discussed in our previous lesson. So this is just a small review of what we discussed previously. Well, let's actually go into the main idea, which is the idea of circles and the lengths of segments. So let's start by discussing some vocabulary words here. So here we have the same diagram as we did on our introduction. And in this diagram, we know that CD and AB are chords. So CD, it's a chord. AB, it's a chord. Now, AP, which it's equivalent to this segment, notice that AP is just a small portion of the actual chord of AB. So therefore, we can call it a segment of the chord of AB. And the same can be said about PB. Notice that PB, it's also a small segment or a small portion of the overall chord. So therefore, PB can be said to be a segment of a chord of AB. So pretty much segment just means a little piece of. And we could also say the opposite. We also can see another segment chords, because now notice that CP, this little piece right here, and also PD are segment chords or segments of the chord of CD. So segments are just mean little piece of. So it's just like we're just looking at a little portion of the overall chord. But this is just a vocabulary that we have to discuss. And why is it that we have to discuss this vocabulary? Because there's a relationship between segment chords of chords. And that's what we're going to be discussing now in our first theorem. Now, the first theorem for today states the following. Here we've been given two chords. They intersect at a point P. Notice that we have two chords. We have the chord of CD and AB, and they intersect at point P. So now notice that we have two small chord segments. Notice that AP, it's a segment of the chord AB, and PB, it's a segment of the chord AB, and the same can be said about CP and PD. And what we're trying to show is that if I get the value of one of those chords, segments of those chords, which in this case is R, so if I get this little piece of a chord and I multiply it by the other segment of the same chord, if I multiply those two chord segments, that's going to be equivalent to T, which can be seen here, times U. What we want to show is that if I get the segments of one chord, if I get both segments of the chord, that's if I multiply them, that's going to be equivalent as if I would have multiplied the segments of another chord in a circle, as long as they intersect at the same point. So this is what we want to show. If I get R and I multiply by S, that's going to be equivalent to T multiplied by U. So let's actually show that this is true. Let's actually show that this is actually a true statement now. So we want to show that this is true. We got to start with a statement and reason. And again, we always want to start with the givens, and the only thing that I know is that AB and CD are chords, and this is the given. But before we go any further, I want to introduce two auxiliary lines. I want to introduce the auxiliary line AD, so AD, and also the auxiliary line of CV and CV. Oops, this is not given, but this is just auxiliary lines. And why is it that I want to introduce them as auxiliary lines? Because now notice that I can think of this as if we were two triangles now. But if I want to think about those two triangles, well, notice that there's a relationship between some angles within those triangles. Because notice that now, if I take a look at this inscribed angle, let's call it A, notice that that inscribed angle has the same starting and ending point than the second inscribed angle. They both intersect in the arc DB. So therefore, I want to call this angle A. So therefore, angle A is congruent to angle C. Because of this inscribed angles, they intersect the same arc. And the arc that they both intersect is DV. So now I know that angle A is congruent to angle C. So what else can we see from this figure? Well, notice that this angle right here, which let me call this angle X, and this angle right here, and let me call this angle Y, they're both congruent to each other. So angle X is congruent to angle Y. And the reason why is it because they're just vertical angles. Let me just clear this a little bit, because what we have shown is the following. We have two triangles. we have two triangles. So let me just highlight the triangles. So we have this triangle right here, and we have our second triangle over here. And what we have shown that within these two triangles, this angle is congruent to this angle, and now also we got these two angles right here, and they must be congruent because they're vertical angles. And now notice that now we can say that those two triangles are actually similar. So triangle ADB, or ADP, I'm sorry, is similar to triangle CBP. And the reason behind it is because now we can use the angle-angle similarity theorem. And since I know that those two triangles are now similar to each other, now I can use those ratios. Because now, notice that the line segment R, which it was right here, the line segment R is corresponding to T, so therefore R over T should be equal to U over S. Let me just, so we got angle D and P, and we got our other triangle C, P, B. We got that this angle is congruent to this angle is congruent to this angle. So now notice that AP, which is exactly R, corresponds to PC because they're both on the opposite of the angle that we didn't show congruency of. And the same idea can be said about PB. So PB corresponds to PD as well because they're both in front of the angle that we just did it with one mark. So therefore we do have this similarity proportion now. And the reason behind it is because of what we just said a couple seconds ago. We know this is true because ADP is similar to CVP. And we're pretty much done. I'm just going to try to finish up this theorem right here. So this is my statement. This is my reason. I'm just going to try to finish it up because now, notice that if we cross multiply, we're going to get R times S. That's going to be equivalent to T times U. And that's exactly what we wanted to show. R times S, it's equivalent to T times U. And let's just recap. Let's just take a look at our final product. All we have said is the following. Given two segments, if they both intersect at a point, the value of this line segment times the value of this other line segment, that's going to be equivalent to the multiplication of this chord segment times this chord segment. And that's a very strong statement to understand. Now we move on to the next theorem that we're going to be discussing today. Before we do that, we want to discuss another vocabulary word, and that is the idea of an external segment. What an external segment is so in the diagram on the right hand side, notice that we have two secant lines. We have the secant line of AP, which we know that's a secant line because it intersects the circle at 2 points. And also we got CP. And now what we want to show is that BP and DP are, well, let's identify where they are. So BP is right here, and DP is right here. They're what we call the exteriors of the circle, and they're referred to as external segments, which is segments that are outside of a circle, which are within a secant line. So notice that AP is a secant line, and the external segment of the secant line is, in this case, BP, and that's what we refer to as an external segment. Notice that PC, that's definitely a secant line, and DP is the exterior part of the secant line, so therefore DP is what we refer to as an external segment. And what we want to show now is that there's a relationship between the overall secant and the external segment. And that relationship is that when we have two secant lines here, if I take a look at the whole secant line, which in this case is represented by R, and I multiply by its external segment, which in this case is S, so the whole times the external, that is going to be equivalent also to the whole of the other secant line times its external. So let's get started. So in two types of secant lines, so the whole times the external, it's equivalent to the other whole times the external. So why is it that this is true? Well, let's see. Let's prove this. And to prove this, let's do a statement in reason. Statement in reason. So first things first, let's identify the givens. So all I know is that AP and CP are just secants. And that's the given. I'm going to introduce two auxiliary lines. Let me introduce the auxiliary line AD. So AD. And also I'm going to introduce this other auxiliary line, CB. And what type of lines? They are chords. Because now, by introducing those auxiliary lines, notice that I have created two triangles. I have the triangle APD, so I can think of this as if it was just a triangle. And also, in addition to that, I also have the triangle BCP. So let's see, what can we say about that triangle? Well, the first thing that can be seen is that if I take a look at this inscribed angle right here, so now notice that DAB, that's definitely an inscribed angle. And this inscribed angle intersects the arc BD. And that is exactly the same arc that this inscribed angle C intersects as well. So therefore, since this inscribed angle, angle A, and the inscribed angle C, they intersect the same arc. Therefore, angle A is congruent to angle C, since they both intersect. The same arc. So therefore, they're congruent to each other. So I think it would be better if I just separate those triangles. So give me 1 second. Now we're back. All we have shown is that angle A is congruent to angle C. But now notice that angle P, which is this angle right here, it is present on both of those triangles. So therefore, angle P is definitely congruent to itself due to a reflexive property. Oops, double. So now notice that we have two congruent angles in both triangles. So therefore, those two triangles, triangle APD, is definitely similar to triangle CPB due to angle-angle similarity theorem. Now if we put, so now I know that those two triangles are definitely similar to each other, but let me actually put the letters of those segments on our figure. So I know that AP, this is represented by R, and we also have the U, this is our U, and in here, this is our T, and in here, this is our S. So now notice since I know that those two triangles are similar now, so therefore I can take a look at their proportions. Because now notice that segment R over T, since they are their corresponding figures, that should be equivalent to U over S. And the reason why is because since they're similar, and we're pretty much done, because notice that we almost had the form here. We gotta have it in linear form. So therefore, I'm gonna just try to finish it up here. Statement and reason. So now for angle 7, notice that if I cross multiply, I'm gonna have R times S. And that is going to be equivalent to T times U. Which is exactly the statement that we wanted to show. Now we want to just recap what we have just shown. What we have just shown is that for any, oops, give me 1 second. So what we have shown is that whenever we have two secant lines, if I get the whole segment of the secant line and I multiply by the exterior part of that same secant line, that multiplication is going to be equivalent to the multiplication of the other secant line times the exterior part of that secant line. And that's what we have just shown. That's exactly what we have just shown here. So let's just discuss, we're not going to prove this, but we're just going to show a small example to just illustrate what this theorem is saying. So now notice that this proof talks about a secant and a tangent line. It states, when a secant segment and a tangent segment are drawn to a circle from an exterior point, which is exactly here, so we have the exterior point, the product of the secant segments and its external segments is equal to the square of the tangent segments. What do we mean by that? Well, this means that if I take the length of the secant line, which in this case, right now my secant line, if I take a look at the whole length of the secant line, that will have a length of 9. So if I take the length of the secant line and I multiply it by its exterior part, which in this case it's 4, that will always be equal to the square of the tangent exterior part. And this will always be the case. I'm sorry, not the square root, the square. Because notice that it states here that it is the square, not the square root. It is the square of the tangent segments. So this will always be the case. When you do have a secant line and a tangent line, and they intersect at a point, there's a relationship. And that relationship is that if I take the whole length of the secant and I multiply by the exterior part, which in this case is going to be 9 times 4, that will always be equal to the square of the exterior part of the tangent line, which in this case is just y. And now that we have it in this case, notice that we can definitely solve for y. Because 9 times 4, that's 36. Y squared. Now to solve for y, now I take the square root. So y is the square root of 36, so that's plus or minus 6. But notice that y represents a length, therefore there's no such thing as a negative length. So the real answer is just 6.